Welcome to the course on analog and digital electronics. So in the very first lecture of analog and digital electronics, we have seen a brief introduction about the subject. Okay. So as I have told you, the subject is divided into two parts. One is the analog electronics part and another one is digital electronics part. And yesterday only we have seen the difference between these two signals. Okay. And according to us, now analog electronics is equally important to that of digital electronics. Okay. Though digital electronics have served some superior advantages compared to the analog electronics, but still analog electronics is in existence because analog electronics will use the signals which are naturally available, which are the physical signals, while in case of digital electronics, we need to convert analog signal into digital one, and then we need to process. Okay, though processing is very much easy and it is prone to the noises or disturbances, right? So we have seen some advantages of analog electronics and some advantages of digital electronics. Okay, so from today now we will start with our basics of operational amplifier, right? So talking about this operational amplifier, they are most commonly referred as op-amp. When we talk about operational amplifier, they are known as op-amp. Okay, so this op-amp were introduced initially in 1940s, right? Okay, so talking about the exact time period, in 1948, the first operational amplifier was designed, and that was using vacuum tubes. Okay, in case of basic electronics also we have seen what is the use of this vacuum tubes. Okay, so talking about the applications of these operational amplifiers using vacuum tubes in 1948, they were used in analog computers to perform the variety of mathematical operations. Okay, so talking about the applications of this is in analog computers, where this operational amplifier was used for mathematical operations like addition, subtraction, multiplication, etc. Right? So now you will understand why it is called operational amplifiers, because these circuits, these amplifiers were used to perform these operations, mathematical operations, and this is the reason why it is known as operational amplifier. Okay, but as you can see, it uses these vacuum tubes, right? So because of these vacuum tubes, what is the disadvantage of using the vacuum tube, right? The disadvantage was vacuum tubes are bulky, okay, and they consume more power. Okay, so power consuming also, they are bulky, power consuming, as well as expensive, right? So these are the some of the disadvantages of operational amplifiers which are made using these vacuum tubes. Okay, so another alternative was under process, right? And they have found the solution in 1964 to 1968. Lot of research were going on, and finally in 1964 to 1968, a scientist named Robert J. Widler at Fairchild Semiconducting Material Company, Fairchild, he brought the most popular 741 integrated circuit. Okay, 741 integrated circuit, now known as IC. Okay, so what they have changed? See, initially, if we talk about the operational amplifiers, these operational amplifiers were made up of vacuum tubes, which are bulky. They consume very much high amount of power and they were expensive. And in between 1964 and 1968, at Fairchild Semiconductor, Robert J. Widler found the IC741, which is made up of transistors like bipolar junction transistors and field effect transistors. Okay, now we know the operation and constructional details of this BJTs and FETs very well. Okay, so what they have done, these BJTs and FETs, they are fabricated along with the other supporting components on a single semiconductor chip or wafer, and the size of this chip was a pinhead, only a single pinhead size. Okay, that is very much small, right? So with the help of this integrated circuit operational amplifier, the circuit design becomes very simple, right? The variety of useful circuits can be built without the necessity of knowing about the complex internal circuitry, right? Moreover, these IC op-amps are inexpensive, they take up less space and consumes less power, right? So these are the advantages which is being offered by integrated circuit, or you can say IC, right? So ICs are inexpensive, it take up less space and consumes less power. And this is the reason why this internal circuit operational amplifier has become an integral part of almost every electronic circuit, okay, which uses this linear integrated circuits. Okay, so talking about the modern linear IC op amp, they works at very lower voltage and they are also low in cost, that millions are now in use annually. Okay, millions and millions of these integrated circuits are used for fabrication and design of electronic circuits. Okay, so there are number of advantages of these operational amplifiers. Okay, let us talk about few advantages as well as applications, right? So talking about the advantages, first and foremost advantage is its low cost, right? Then very small size. Okay, then they are versatile. So versatility and flexibility are some of the advantages, and dependability also. Okay, so these are the advantages which is being offered by operational amplifiers, and they are being used in certain applications. So you will find the use of operational amplifiers in process control, then communication circuitries, then in computers definitely, then in sources. Say I talk about the power source or signal source. Okay, then some measuring instruments are also there, some displays are also there. So in each and every electronic component you will find these integrated ICs, right, which is nothing but it is used for some mathematical operation like addition, subtraction, multiplication, etc. Okay, so talking about the op amp, it is nothing but basically an excellent high gain DC amplifier. Okay, op amp is nothing but excellent high gain DC amplifier. Okay, see, we are talking about this amplifier. What do you mean by amplifier? Whenever we are giving some input of very small signal, the output of this amplifier will be large. Okay, so suppose I am talking about in terms of voltage. Say my input is 1 volt, then output may be 5 volt, 10 volt, etc. depending on the gain offered by this amplifier circuit. That is what we have seen in applications of MOSFET, applications of field effect transistors, and applications of bipolar junction transistor. Okay, so one of the application of this semiconductor devices is used as an amplifier, where a very small input signal can be raised to a certain level, that is high output signal, by some gain. Okay, so we have to find out the amount of gain offered by this particular circuit. Right? So to understand this operational amplifier better, we will start with the basics of differential amplifier. Right? This differential amplifier is the basic building block of integrated circuit op-amp. Hence, we will analyze the differential amplifier first and their supporting circuits. Then we will move on to the actual integrated circuit, that is IC 741. Right? So we will start with the basics of differential amplifier. Right? Now, what do you mean by differential amplifier? Okay, anyone? Okay, basically, as the name suggests, whenever we talk about the differential amplifier, it amplifies the difference between the two input voltage signals, and this is the reason why it is called difference amplifier. Okay? So differential amplifier amplifies the difference between two input voltage signals, between two input voltage signals, and this is the reason why it is also known as difference amplifier. Okay, so let us start with the basic, or you can say ideal differential amplifier. Right? Okay, so we'll start with the block diagram of this ideal differential amplifier, then we'll move on to the actual circuit. Right? What do you mean by ideal circuit? Whenever we talk about the ideal differential amplifier, that means whatever ideal parameters are there, that we will be considering. Okay, so differential amplifier will have two number of inputs and single output like this. So this circuit is our ideal differential amplifier. Right? Let us say I am giving some input V1 to terminal 1 and input V2 to terminal 2. Okay, so this is grounded terminal, this is also grounded terminal, and here also we will have grounded terminal, where I am going to measure some output V0. Okay, so here you can see two inputs V1 and V2 are available. Okay, so the actual input will be the difference between those two inputs. Let us call this difference as VD. Okay, so VD here will be my difference input voltage, right? And its magnitude is equal to V1 minus V2. Okay, so this is the amount of voltage which is given at this terminal, that is input terminal. Okay, so now what will happen? V1 and V2 are the two input signals, while V0 is the single-ended output. Okay, so each and every signal we are measuring with respect to the ground. Okay, so in an ideal amplifier, differential amplifier, the output voltage V0 will be proportional to the difference between the two input signals. Okay, so talking about the output voltage V0, that is proportional to the difference between two input signal, that is V1 minus V2. Okay, so suppose V1 is 5 volt and V2 is 3 volt, then 5 minus 3, it will be equal to 2. So you can say ideally my output voltage V0 is equal to 2 volt. Okay, but as I have told you, this is amplifier circuit, right? And amplifier circuit, what it will do, it will amplify the input signal and it will raise the magnitude of the input. Okay, so suppose we are providing 2 volt Vd equal to 2 volt, then output must not be equal to 2 volt, it must be greater than this 2 volt. Then and then we will be able to call it as an amplifier circuit, right? And this is the reason why one term came into the picture which is known as gain. Okay, so suppose I tell you that this particular circuit, amplifier circuit, has gain of 5, which means my output will be 5 times more the input. Okay, so suppose my differential input is 2 volt now, then output will be equal to 10 volt. Okay, suppose gain is 10, in that case 2 volt input will converted into 20 volt of output. Okay, so this is the importance of gain, right? So we are available with one gain. In this case, the gain is known as differential gain. Okay, we will call it gain AD. Right? So let us now understand what do you mean by this differential gain. It is denoted by A suffix D. Okay, so we have this equation. Let us call this as equation number 1. Right? So from equation number 1, now I will be able to write down this as V0 equal to AD. Okay, I am taking the proportionality constant AD into V1 minus V2. Right? So here what I have done, this AD is nothing but constant of proportionality. Right? So this AD is nothing but the gain with which differential amplifier amplifies the difference between two input signals, and this is the reason why it is called differential gain of the differential amplifier. Okay, so AD is nothing but, we may say, differential gain of amplifier. Okay, and here the difference between the two input V1 minus V2 is generally called V1 minus V2 is generally called difference voltage, and it is denoted as V suffix D. Okay, so ultimately now we will be able to write down our equation of V0 as AD, which is my differential gain, and VD, which is my difference voltage. Okay, so this is the equation, output equation of differential amplifier, right? Let us call this equation as equation number 2. Okay, so now we know very well that my output will be AD times the input voltage, which is difference voltage in this our case. Okay, so we will be able to calculate the gain now. So gain AD is nothing but the ratio of output voltage to the input voltage. And when we talk about this differential gain AD, it is expressed in its decibel value. Whenever you will find out the differential term, you will find out that it is generally the differential gain AD is expressed in decibel, okay, that is dB. Okay, so AD is equal to 20 log to the base 10 of gain AD in decibel. Right? So suppose you have to represent the differential term gain, then you need to represent this differential gain in terms of decibel. Okay, so this is about the differential gain, right? So now if you know the amount of input voltage, if you know the value of differential gain, then you will be able to predict the value of output voltage V0, which is equal to AD times VD, right? So this is not the only gain which is associated with this difference amplifier. Okay, we were talking about the differential gain. Similarly, we have to consider another kind of gain which is known as common mode gain, right? So there is one more gain associated with the amplifier circuit, which is common mode gain, and it is denoted by A suffix C. Okay. Now let us try to understand this common mode gain. Okay. Suppose we apply two input voltages which are equal in all the respect to the differential amplifier. Okay. So I am talking about the case where my both the inputs, input V1 and input V2 are same. Okay. So when this is the case, at that time what will happen to output voltage? According to our equation of output voltage, V0 is equal to AD times V1 minus V2, right? So if V1 and V2 are same, in that case our output voltage V0 would be equal to 0. Okay, this is 0. Okay, but actually what happens, the output voltage of practical differential amplifier not only depends on the difference voltage, but it also depends on the average common level of the two inputs. Okay, and such an average level of the two input signals is called common mode signal, which is denoted as Vc. Okay, so I am talking about the output of this particular circuit V0 over here. Okay, this output is clear cut, nothing but the difference between the two input signal, that is V1 minus V2. That is what we have seen in case of ideal amplifier. But whenever we are having a practical circuit, if we talk about the practical difference, okay, so this average level of the two input, average level of the two input signals is called common mode signal, called common mode signal, and it is denoted as Vc. Okay, so now what is common mode signal? Okay, if we talk about Vc, then Vc is equal to V1 plus V2 by 2. Okay, this is my common mode signal. So practically the differential amplifier produces the output voltage that is proportional to such common mode signal also. Okay, the output does not depends on different signal V1 minus V2 only, but it also depends on this common mode signal, or you can say common mode voltage Vc, which is nothing but the average of two input signals V1 plus V2 by 2. Okay, so now my output voltage equation will be another, that is V0 is equal to AC times Vc. Okay, so the gain with which it amplifies the common mode signal to produce the output is called common mode gain of the differential amplifier and denoted as AC. Okay, so now here we have introduced the new gain, which is known as common mode gain, denoted by A suffix C. And this is the reason why we will be available with this equation of output voltage V0 equal to AC times Vc. Okay, so here you can say there exists some finite output for V1 equal to V2 due to such common mode gain AC in case of practical differential amplifier. Okay, so whenever we are available with one DC differential amplifier, and if you made these two input signals same, that is V1 equal to V2, still we will get some output voltage because of this common mode signal and common mode gain. Okay, so ultimately we can say, if I talk about total output of differential amplifier, practical differential amplifier we are talking about, so the total output of any differential amplifier can be expressed as V0 equal to ADVD plus AC Vc. Okay, so this will be our output voltage of practical differential amplifier. Okay, now if you look back at this equation carefully, let us call it equation A. Okay, so it shows that if my one input is, suppose let us say our one input is plus 25 microvolt, right, and another input is minus 25 microvolt. Okay, this is my V2 and this one is V1. Then what will be the output? The output of the amplifier will not be the same with the input such as 600 microvolt and 650 microvolt. Right? Okay. See, in this case, if I talk about the difference between V1 and V2, let us say, what is V1 minus V2? 25 minus 25 microvolt, that becomes 50 microvolt. And here difference is V1 minus V2 is equal to 600 minus 650 microvolt. This is also 50 microvolt. Okay, so we have considered these two different cases, but here you can see the difference between the two sets of input is 50 microvolt only. Still the output will not be equal to same. Okay, so for an ideal differential amplifier, the differential gain AD must be infinite, while the common mode gain must be equal to 0, and that will ensure the zero output for V1 equal to V2. Okay, ideally it should be 0, theoretically it should be 0 whenever V1 is equal to V2. For that case, what happens? You should have differential gain equal to infinite and common mode gain AC equal to 0. Then we will get output voltage V0 equal to 0 in case of V1 minus V2, V1 equal to V2. But what is the problem? Due to the mismatch in the internal circuitry, there is some output available for V1 equal to V2, and hence gain AC is not practically 0. Okay. So the value of such common mode gain AC is very small, while the value of the differential gain ADE is always very large. Okay. So at this stage, we can define one of the most important parameter of the differential amplifier, which is known as common mode rejection ratio. Okay. So you need to understand this parameter, which is known as common mode rejection ratio, known as CMRR. Okay. So consider we have applied same voltage to both the inputs. Okay. So you can say now our differential amplifier is said to be operated in common mode configuration. Okay. So many disturbance signals, noise signals appear as a common input signal to both the input terminals of the differential amplifier. Okay. And such a common signal must be rejected by the differential amplifier. Okay. See, I have talked about the noise. Okay. Yesterday only we have seen the effect of noise in case of analog circuit, right? Output changes tremendously, right? So this noise must be rejected, and this is the reason why we have introduced this parameter or this ratio, which is known as common mode rejection ratio. Okay. So common mode rejection ratio is nothing but it is the ability of a differential amplifier to reject the common mode signal. Okay. So it is the ability of a differential amplifier to reject a common mode signal, a common mode signal, right? And it is expressed by a ratio which is known as common mode rejection ratio, which is denoted by CMRR. Okay. So CMRR is nothing but CMRR is defined as the ratio of the differential voltage gain AD to the common mode voltage gain AC. Here AD is equal to differential voltage gain and AC is common mode voltage gain. Okay. And this CMRR is denoted as rho. Okay. So ideally, common mode voltage gain, what is it? It is 0. Hence, the ideal value of CMRR would be infinite. Okay. If I talk about the ideal case, ideally what will happen? CMRR rho will be equal to AD. AD we will have some large value and AC is equal to 0. So 1 over 0 becomes infinite, and that is why the ideal value of common mode rejection ratio would be infinite. Okay. But for a practical differential amplifier, this AD is large and AC is small. Hence, the value of CMRR will also be equal to very large. Okay. sometimes you will find that CMRR is also expressed in decibels. Okay, so we will also try to express common mode rejection ratio in decibel. It is given by 20 log AD by AC decibel. Okay, so this is our parameter common mode rejection ratio. Now, using this parameter, let us try to define the output voltage. Okay, so we will try to define the output voltage in terms of CMRR now. Okay, so we have this equation, output voltage equation V0, which is given by AD times VD plus AC times VC. Okay, so let us take AD VD common out of this equation, then it will be equal to 1 plus AC VC divided by AD VD. Okay, so now our output is 1 plus, what is CMRR? CMRR is ratio of AD by AC. Okay, so what I am doing, I am writing down this term as AD by AC over here into VC by VD. Okay, so this denominator term in this equation is equal to CMRR, right? So our output voltage V0 will now be equal to ADVD into 1 plus 1 over CMRR into VC by VD. Okay, so this is how we can express the output voltage equation of differential amplifier in terms of common mode rejection ratio. Okay, so this equation explains that as CMRR is practically very large, though both VC and VD components are present, the output is mostly proportional to the different signal only, you can see. Okay, so the common mode component is greatly rejected. Here you can see if I talk about this V0, then V0 is equal to AD times VD, and here CMRR, the value of CMRR is very large according to us, right? Ideally it is infinite, and practically it is very much large, and this large value is in terms of it is in the denominator of the equation, such that this entire component, okay, I'm talking about this component, this entire component becomes very much small compared to this AD times VD. So ultimately we can say output voltage is directly proportional to difference voltage of the two inputs. Okay, so from this we can say that the common mode signal VC has been rejected almost. Okay, though small value will definitely appear, but it is largely rejected, greatly rejected, and that is why this is important in case of analog electronics. Okay, so we require our common mode rejection ratio as high as possible to reject the common mode signal. Common mode signal is not desired. Okay, this is not the desired signal. It is available because of the noises and disturbances in the input signal, right? And this is the reason why it must be rejected. Okay, so with the help of this CMRR, we will be able to reject this common mode signals, right? So this is how this differential amplifier will work. Okay, so now talking about the features which are offered by this amplifier, right? So let us talk about some features of differential amplifier. Okay, so talking about the features of differential amplifier, we have the first feature, which is high differential voltage gain. High differential voltage gain. Okay, this is what we have seen. Second, if we talk about common mode gain, then the value of common mode gain is low, right? So we have very low common mode gain, right? Then talking about the CMRR ratio, then we have high value of common mode rejection ratio. Okay, then this is the differential amplifier. Okay, so we have two input terminals. So this is also feature. It has two input terminals. Okay, then talking about the input impedance. Okay, so input impedance offered by this amplifier is very much high. Okay, and this is advantageous, high input impedance, right? See, what do you mean by impedance? Impedance is the one kind of resistance offered by the device. Okay, so if my input impedance is very much high, you can see, coming back to the block diagram. Okay, so I am talking about this terminal, terminal number 1. This is my input terminal. So if we provide very high input, in that case what will happen? In case of absence of supply voltage V1 and V2, current flowing through it will be equal to 0, and this is desirable, right? Because of the high input impedance. If input impedance is very much low, then what will happen? As we have discussed, common mode signal is always available, right? So this common mode signal will cause certain amount of current to flow through the input terminals, which is not desirable at all. If we have not switched on the supply, then current must be equal to 0, and current will be equal to 0 when the input terminal offers the very high impedance. Okay, so this is one of the features of differential amplifier, that it has high input impedance, right? Then talking about the bandwidth, it will have a very large bandwidth. Okay, bandwidth is nothing but the range of frequencies in which your circuit can operate. Okay, as we will move on, we will see, we'll try to understand this thoroughly, the bandwidth. Okay, then it has low offset voltages and currents. Low offset voltages and currents, right? So we'll try to understand what do you mean by this offset voltages also and offset currents also as we move on. And then talking about the output impedance. Okay, so output impedance must be low in any electrical or electronic circuit. Why it must be low? Because suppose we are available with this circuit, right? This is my electronic circuit, right? Now I have two inputs V1 and V2, and I have one output V0 over here, right? So we will be able to connect some load at the output terminal, okay, having some value of RL. Now suppose the impedance of the output terminal is higher, then what will happen? The voltage appears across this load resistance will be lower. Okay, suppose this is my output impedance R0. Okay, so the value of output impedance is high, then there will be a voltage drop across this impedance R0, right? So ultimately the voltage available at the output terminal will be reduced, and this is not advantageous, and this is how, that is why output impedance must be as low as possible. Okay, so we will have this low output impedance, right? So these are the various features of differential amplifier. Okay, now talking about the construction of differential amplifier, then we will use transistor as a switch in this case. Okay, so we will have some emitter biased circuit. Two emitter biased circuits are connected in such a way that we will be able to get differential amplifier, right? So before we start with the circuit configurations of differential amplifier, let us have a small example such that we will get the clear-cut idea how we are going to use these parameters: common mode gain, differential gain, common mode rejection ratio, etc., etc. Right? So we are available with one differential amplifier. Okay. So what you need to do is you have to determine the output voltage of a differential amplifier for the input voltage of is of 300 microvolt and 240 microvolt. Okay, then differential gain ADE of the amplifier is 5000, right? Then value of common mode rejection ratio CMRR is given to you 100, and in second case consider CMRR equal to 10 raised to 5. Okay, so we are available with these two cases. When CMRR equal to 100, at that time find out the output voltage of a differential amplifier, and when CMRR is equal to 10 raised to 5, at that time you need to find out the output voltage, right? So we have been given one differential amplifier. Okay, so we have these two inputs over here and we have one output over here. Okay? This is my input V1, which is equal to 300 microvolt, and input V2 is 240 microvolt. And we need to find out the output voltage over here. Now differential gain AD is given to us 5000. Okay. Then there are two cases. One, when CMRR equal to 100, at that time what is output voltage? And second case where CMRR equal to 10 raised to 5, calculate the output voltage. Okay. In order to get the output voltage, what we require? We require the value of AD, which is already given to you, but we don't know the value of AC. Okay. Then we have to calculate the value of VC. Now we know we are available with the two input terminals V1 and V2. So VC will be equal, VC is nothing but the average value of the two input terminals, right? So we have these equations of VC equal to V1 plus V2 by 2. Okay, all the parameters are available to us. AD already available to us, it is equal to 5000. V0 we need to find out, and then differential voltage VD is also available too. It is V1 minus V2. So the remaining is AC. Okay. So how will you find out AC? Now there is one term which is given to you is CMRR. Okay, and we know very well that CMRR is nothing but the ratio of differential gain AD to common mode gain AC, such that we will get the value of AC equal to AD upon CMRR. Right. So now all the parameters which are required to find out the desired value we are available with. Okay. So let us start with the first case. where we have value of CMRR equal to 100. Okay, so differential voltage in that case is equal to V1 minus V2, which is equal to 300 minus 240 microvolt, which is equal to 60 microvolt. Okay, then common mode voltage Vc is equal to V1 plus V2 by 2, so it will be equal to 300 plus 240 by 2, 640 by 2, sorry, 740 by 2 will be equal to 270 microvolt. And then AC is equal to AD upon CMRR. Okay, AD is given to you 5000, CMRR in this case would be 100. So common mode gain will be equal to 50. Okay, so all the parameters which are required to find out the output voltage is now available to us. So put these values in equation of output voltage. AD is equal to 5000, VD is equal to 60 microvolt, plus AC is equal to 50 and VC is equal to 270 microvolt. And the final answer will be 313.5 millivolt. Okay, that should be our first answer when the value of CMRR is equal to 100. Okay, then consider the second case where we have been given the value of common mode rejection ratio is equal to 10 raised to 5. Okay, so VD remains same in that case, VC remains same, the changes will be in AC, common mode gain. So AC is equal to AD by CMRR in this case. So AD has been given to us 5000 and this time CMRR is 10 raised to 5. Okay, so AC would be 0.05. Now see the difference. Okay, whenever CMRR is 100, at that time common mode gain was 50, and whenever we increase the value of CMRR, you can see the change, drastic change. Okay, so as the value of common mode rejection ratio is high, common mode signal will be highly rejected in this case. Okay, so we will see a clear-cut difference in the output voltage now. Okay, so we have V0, which is equal to AD 5000, VD difference voltage is already available to us 60 microvolt, plus AC 0.05 and VC 270 microvolt. Okay, so output voltage will be 0.05 into 270 into 10 raised to minus 6. That will become 1.35 into 10 raised to minus 5. So we will have output voltage 300,013.5 microvolt, or you can say 300 plus 0.0135 millivolt. Okay, so this will be the output voltage when we have increased our CMRR value. Okay, so ideally we can say common mode gain AC must be equal to 0 and output should be only ADVD. Okay, so what is ADVD in this case? Say if I talk about this ADVD. Okay, so ADVD is equal to 5000 into 60 into 10 raised to minus 6, and which is equal to 300 millivolt. Okay, so my output should be equal to 300 millivolt if I consider the ideal case, and that is what we are getting. If you see, the output voltage is nearly 300.0135 millivolt. Okay, so we can say that we have almost rejected the common mode signal or noise or disturbance. Okay, so this is how you will be able to calculate all the required parameters in case of differential amplifier. Okay, so we have seen some basics of differential amplifier today. We have gone through some important parameters which are differential gain, common mode gain, then common mode rejection ratio, CMRR, which we will be frequently used in the analysis of all the differential amplifier circuits. Okay, so we will stop here for today. In the next lecture, we will continue with this basics of differential amplifier. In this case, we will try to configure one circuit of differential amplifier with the help of these transistors and BJTs. Okay, and then we will analyze that particular circuit, and we will see in which configurations you will be able to operate these differential amplifiers. Okay. Okay, so we'll stop here. If you have any questions, then you are free to ask.
Hello, sir.
Yes.
Sir, lecture recording the Teams માં નથી બતાવતા.
I have not uploaded yet. Okay, હું આજ સાંજ સુધીમાં બંને લેક્ચર અપલોડ કરી દઈશ.
Okay, sir. Thank you, sir.
Thank you, sir.
Okay, કોઈ questions છે? Okay,
No
so
questions, sir. Thank you.
okay, thank you for joining. We'll stop here.